join discord.gg/flatearth and enter a check-in room. Someone will come along and verify you to get involved in the conversation about our
Earth. Between A and B, personally. I don't think A is the horizon, by the way. I don't think A is the horizon.
Oh, you don't?
No, it's if you look at the full footage, it's not. It's nowhere near a straight line across. Like, it's all wobbly and shit. So I don't think A is the horizon. I think habitat is obstructed a tiny bit.
I can post the video if you'd like.
Oh, I've seen the video, yeah.
Oh, you've seen the video too?
Yeah.
All right, so what's your thoughts on how far is the horizon supposed to be?
Depends on the atmospheric conditions.
Really?
Depends on the refractive gradient.
Refractive gradient. So when does refraction begin?
As soon as a photon hits a molecule of the atmosphere.
All right. Well, how do you get refraction to begin?
Say again. Your audio's pretty shit.
How do you get refraction? How does refraction occur?
Yeah, so photons hit molecules of the atmosphere. Have you heard of the analogy of the marching band with refraction?
No.
Okay, so marching band.
Before we go into that, you're going to have to define refraction, and you're going to have to define Snell's law.
You probably shouldn't use Snell's law for the atmosphere, but we can if you like. Yeah, so refraction is light bending through changing densities.
Bending?
Yep.
Bending, or the angle changes?
Yeah, that's fine. Yeah, there are billions of little tiny angle changes. Yes.
It doesn't curve, right?
Oh, well, if you zoom out from a density gradient, yes, it does curve. But when you zoom in, there's all these millions and billions of little different angle changes. Sure.
You realize the density gradient occurs vertically; it doesn't occur horizontally.
Yes. Correct. Yep.
So then, where's the gradient that's going to cause refraction going out horizontally?
Because there's more molecules below than there are above. That's why I asked about the marching band analogy.
But the medium is the same all the way out.
No, there's more molecules below than there are above.
But the medium.
Right, so, can I explain the marching band analogy? Then this will make sense.
But that's not how refraction works.
It is. It actually is.
It is not.
So the marching band analogy.
You have to have a change in medium in order for refraction to work.
At a macro level, you can use Snell's law with sort of gradiated, discrete layers of the atmosphere.
So
there are issues with that mathematically. That's why you use Fermat's principle.
So when there's fog, then there's just too much refraction going on for me to see anything?
Oh, it's usually scattering. If it's fog, you just can't see shit.
Come on, man. You're reaching for an explanation just so that way you don't have to say the Earth is flat.
If I explain the marching band analogy, I think you'll understand why, even if you are pointing light directly horizontal, why it will still refract downwards. If you understand the marching band analogy, which is kind of close to how refraction works.
I've done your marching band analogy, and I would think that scatter would occur a lot more than refraction.
Oh, scatter does occur, yeah.
Yeah, but you don't see scatter occurring in the image.
Light is scattering, right? But it's not enough distance to scatter it all away.
Oh, just 10 miles, that's it.
Yeah, that's not very far.
That's like 50,000 feet.
Right. You don't think you can see 10 miles?
Shoot, I've seen the weather advisories and I can see 25 miles.
Right. So why do you think the light would be scattered away at 10 miles?
Because you claim density.
Right, a density gradient, an optical density gradient, yes. That's there regardless of whether there's fog.
It doesn't explain refraction. Refraction requires some kind of a change in the atmosphere.
Yes, there is a density gradient. And again,
Vertically.
if I get to the... Yes, right, exactly. If I get to the marching band, right, correct. That's how it works, yes. There is a vertical gradient.
Mm-hmm.
That's how it works.
Mm-hmm.
Okay, so can you imagine... there's a good video on YouTube about the marching band. Let me find it. It's basically if a marching band, like there's a row of 4 marchers or whatever playing their instruments, and they hit mud at an angle, right? So the marcher, the person on the inside will slow down, right? The person that hits the mud first will slow down, but the people that haven't hit the mud yet, continue at their speed until they hit the mud, and that causes a bend in the marching band. I need to find the video I can't explain it in words. I'll find it.
It's the same air all the way across the water, man. There's nothing different.
Understand, but there is a density gradient.
No, vertically. There isn't.
Yes, there is. There is
vertically. Yes, vertically.
Yes,
not horizontally.
Right. I agree. It is the vertical gradient that causes it to bend down.
So the upward gradient causes it to bend down. That seems counterintuitive.
No, it's how it works. Okay, I found... Yeah. I'll stick it in the chat anyway. That's kind of the marching band analogy. In the chat.
Marching band to explain light refraction.
Yes. All right. As a photon hits...
Why don't we use light to explain light refraction?
Yeah. Okay. So a light, as a photon, it's traveling, and it's
marching bands to explain. Okay.
Yeah, it's an analogy, but I can explain it with the actual molecular interaction if you like.
Let's say we have explain it with an actual demonstration.
Yeah, I'll explain it. I can't show you in my hands a molecule and a photon hitting it. I can explain what happens. Donato, that is a shit image. That is not how refraction works.
I can show you in my hands the Earth spinning and the water being held to its surface, but if you can imagine it.
You sound like God there. He's got the whole world in his hands.
So Donato.
The whole world in my hands.
Donato in the chat.
I want to hear.
Donato in the chat. That's not how refraction works. It's not gradient horizontally. It's not how it works.
Bro, we're not talking
about gradient horizontally.
I agree. That's why that diagram in the chat is shit. Because that's not how it works.
You would need a horizontal gradient in order for it to bend.
No, you need a vertical gradient. Let me post something. Do I have image perms? Hang on.
I don't know.
Just find out, do you?
I'll find out in a second.
You shouldn't have.
No, you don't.
Boo.
Someone really needs to get an image.
Yeah. Who can I send it to?
You can send it to Sheepdog. I'll post.
Okay.
You can explain it, and then we'll try and figure it out in our heads, and go, well, that's bullshit.
All right. There's Snell's Law. Snell's Law sent to Sheepdog. I want to post that in the chat. That'd be lovely.
I suppose if we're going to go all the way, we may as well go on. Like, if we may as well see what he's trying to represent.
Yes.
With pixels and cameras and angles.
No, just with a Snell's Law.
I want to hear the mark.
Did you send it?
Yeah, it's in your DMs.
Oh.
Tomorrow analogy.
Oh, there it is.
Oh,
So-
come on.
Come on, you cunt.
Come on, cunt. Come on, cunt.
There you go.
There we go.
Go ahead and walk me through it.
All right, so that's Snell's law. And this is, I have to stress, it's a simplification of the atmosphere. But the lower density, the lower refractive index is at the top, generally.
Yeah.
And it's more dense, generally
Okay.
below. Okay.
Right. We have not. You see the first one you posted? The water's flat, bro.
What? It's not water, that's air.
The blue stuff is flat.
No, that's just more dense atmosphere. So more dense atmosphere below, the dark blue, less dense higher up, light blue. All right, so let's say our light beam's coming from the left, traveling to the right, and it's hitting the boundary at 90 degrees. We just do Snell's law, and it bends towards the denser medium. That's the rule of Snell's law, bends towards a denser medium. Even if the light is traveling in an upwards direction, the direction that it bends is towards the denser medium.
Right. So, okay, you're getting bogged down in mathematics, in stuff that doesn't really matter, because logically we can see and prove that the Earth is not a ball. It's not moving. Water does not adhere to the exterior of a ship. I don't know.
I got this.
Okay. All right. Okay. But it's bogging us down in bullshit.
No, I
Yeah,
know he is, because he's gonna claim like the infinite gradient, and so there's an infinite bend of refraction or infinite refraction index.
No.
For Earth ball, right?
You've heard the word infinite, and you've heard the word refraction, and you heard the word Roohif.
Is that
None of
supposed
you
to be a
understand
water
what I
hill?
mean.
All right. So
What?
let me ask you this. Now can you give you a demonstration?
I can explain to you what happens at a molecular level, and I can show you the.
I need
I
a
can
demonstration of this occurring.
Demonstration.
So we
Sorry,
can
guys.
induce-
Sheepdog, just 2 seconds, Roohif. Sheepdog, your microphone's a little bit dodgy, dude. Don't be
Yes,
too
shit.
close or too far away.
Say again. I'm sorry.
Oh, that's brilliant. Stay there. Don't move a fucking muscle. Your microphone was shit before. Now it's perfect. That's all, buddy.
Yeah.
Oh, my voice. Sorry. Anyway, yeah, no, I'm gonna need a demonstration now. I don't need an explanation. I need a demonstration
Sure, of refraction happening where we've induced a density gradient.
with this density gradient,
Yeah, so
Like
I'll give you
gaseous-
examples.
a gaseous density gradient.
Sure, one of these is a gas, yeah. Actually, more of them is a gas. There you go, I DM'd it to you. So one of them is the sugar water, one of them is inducing a horizontal density gradient. Dang Joss does liquid nitrogen to induce a density gradient. Greater Sapien uses temperature to induce a gradient.
So fluid is your demonstration, not gas.
No, I've used Dang Joss, who used liquid nitrogen, which evaporates in a matter of a second. So it's a gaseous gradient. Greater Sapien has used temperature to induce a gaseous gradient. And Mick West has used temperature to induce a horizontal gradient.
What is naturally occurring about those things?
Didn't hear gravity.
What's unnatural about it? What do you define as natural and unnatural?
Well, obviously they had to be isolated and purified, right? So what's natural about it?
Okay, you want it happening in reality? Sure. Like in nature? I've DM'd that to you then.
Oh my God. So you're going to use that as your explanation. You're not going to show me with a laser, show me bendy laser going through the natural air, right?
Bottom right, taboo conspiracy, bendy laser through natural air. You want to post that in the chat?
Bendy laser, natural air.
Yes. Bottom right.
That's scattering. That's not bendy laser.
That's a bendy laser. Come on, champ. Come on. Come on. I'll even post the source video so you can verify for yourself that it's bendy laser. Taboo conspiracy, 16.4 miles.
Is that the one where it's bending up?
Taboo conspiracies, yes. Yeah.
Not bending down.
No, I'm not focused on the name, bro. I'm asking if this was the one where the laser bends up.
Yes.
Okay. Why is it bending up?
Because it's an inverted density gradient. Oops, that's the... Boom. Let me post the link in the chat. There we go. Oh. Yeah, so if you watch that video, you'll see most certainly the laser is curving.
This is the video that the concavers like to use. Say that we're on an inverted surface.
I'm not sure how they would use it for that, but sure.
Oh, come on. You've been in Tartaria. You've had conversations with the concavers.
I actually tried to avoid concavers.
I find that an insult. Like they're not as bent as us.
Yeah, they're a little nuttier. Anyway, sorry, the marching band analogy when it comes to the molecular interaction. Let's say a photon's traveling horizontally and it hits the absolute dead center of a molecule, then it should go straight or be absorbed and re-emitted, whatever. Let's say it's traveling horizontally and it hits the top of a molecule and gets dragged downwards. All right, so that'll cause a change in direction.
Right.
Yep. So if you hit the top of a molecule, the molecule's below you.
Roohif, no.
So the world is a molecule?
You use the mud analogy, right? As the marching band moves to the mud, they kind of like turn inward towards the mud. But you're going from a density gradient higher to a density gradient lower. So wouldn't it scatter if they come out of the mud?
It's only meant to explain the change in direction.
I know, but you use an inverse explanation. So I mean, come on, dude.
Well, I'm trying to give you an analogy for what happens in the atmosphere with the molecules.
Oh, I know. It's a poor analogy. I get it though.
Okay, well then, yeah. So if the photon hits the top of the molecule, it gets dragged downwards. So it changes the direction to point downwards. If it hits the bottom of the molecule, it gets dragged upwards. Cool. Yeah.
So what you're saying is in this laser experiment where bending upward, then it's just hitting the tops of all of the molecules. Is that what's going on?
Not all of the molecules, right? But in a typical gradient, it's actually the other way around. So in a typical gradient, you've got more dense below you and less dense higher up. Mm-hmm. Statistically, you are going to hit more of the tops of molecules than you are the bottoms of molecules. So statistically, you'll more often bend downwards than you will upwards.
Oh, so if it gets lighter as it goes up?
Not sure how to respond to that. I thought I explained it fairly well.
I mean,
if the gradient is more dense below you and less dense higher up, statistically, you're going to hit more of the tops of molecules and bend down than you are hitting the bottom and bending up.
So it's bending off the tops of molecules? Bending downward off the tops of, it's bending downwards off the tops of molecules?
Yep, and upwards off the bottom. And you're going to hit more of the tops than you are of the bottoms in a typical density gradient.
Oh. Yep. I still don't see it.
Okay. Which bit don't you get?
All right. So where's your proof of curvature then?
Sure. If I go to the top of a mountain and I know what my elevation is, and I know another mountain off in the distance and I know its elevation.
Please don't tell me a theodolite.
Yes, a theodolite. Measurable drop.
You love big tunes, don't you?
This is my theodolite measurements. I did this years ago.
I wish you'd come in here and have a conversation with God Rockin'.
Sure, I've spoken to him before. In fact, when was my video put out? Let me check.
Bro, you're off your tuss. You believe that's proof of anything? It's just
Epic. I did mine in
bend the lasers.
June 2019 was my theodolite video.
And so what's the range on your theodolite?
I can see it. I can measure an angle to it. Fuck my voice. There you go. There's my video in the chat. Theodolites don't have a range. They're just angle measuring devices. If I can see it through the scope, I can measure an angle to it.
And how do you be precise with it?
You be as precise as you can see. Should be within about 10 arc seconds. If I had a really good theodolite, I'd get within 1 or 2 arc seconds.
And so what does that prove exactly as far as, go ahead and walk me through it.
Okay, I can make a prediction for the angle that it should be if the Earth is flat, and I can make another prediction for what it should be if the Earth is a globe, if there's drop. And I go and measure it, and it matches the globe prediction. I measured drop.
From where?
From one mountain to another.
Wait,
known
what?
elevations. Let's say I'm at a mountain. Let's say I'm at 1,000 meters elevation, and I look across to another mountain that's also at 1,000 meters. All right, so it's the same elevation.
Wait, so we're not measuring the sun anymore, or doing curvy angles. We're measuring one mountain to another.
Yes.
Okay.
Measuring an elevation angle.
Oh, okay, I see. Because or curve. Okay, all right.
Right. Yeah. So if I'm in a flat Earth, and I'm at 1,000 meters, and the other mountain's 1,000 meters, theoretically I should measure 0 degrees elevation. Right.
Well, how far away is the mountain?
However far? 30 kilometers, 50 kilometers. Long way away.
What about 80?
It's a bit far to see with.
You can't see it, right? Right. Okay. All right. But people do see. But people do see things that should be hidden behind a curve.
I disagree with that.
Well, I mean, it's fucking. Hang on a minute. What's the word I'm looking for? Hang on, I'll find it. Documented.
Okay.
It's documented. We see things too far. So now you're talking about from one mountain to another that's 50 kilometers away, but people see things that are way too far away, right? Okay, so let's just stop right there. Let's just stop right there. What are you trying to do?
With these measurements, it's a measurement of drop. So 8 inches per mile squared.
Right. So if we are seeing things that are way too, like 80 kilometers away, where's your drop?
At 80 kilometers?
It's drop. The drop it's way beyond the drop. So I don't know what you're trying to do here, bro.
Well, do you understand that if on a flat Earth, and we ignore the atmosphere for now, on a flat Earth, if we're both at the same elevation,
can't ignore
then
it,
I should measure 0 degrees. Well,
no, you
just for now.
Okay, all right.
That's
fair enough.
Assuming that they're both the same height, man.
Yeah, so it should be 0 degrees, right?
Well,
assuming they're both the same.
There's going to be some fucking drop. But why are we seeing things that shouldn't be there?
Well, show me something you think shouldn't be there.
All right. Well, you get your thermal light out and you tell people that they can't see things across the fucking Great Lakes of Michigan or fucking mountains that shouldn't be there, or across the mountains of Hawaii, that should not even be there. You shouldn't even see the tops of them.
Show me one.
What?
Show me an example. Yes.
You ever seen them?
I've seen stacks. I've never seen one that is not possible on a globe.
Well, here's my thing. You claim refraction over water, but then you won't claim refraction when you're using a theodolite?
I said just to ignore the atmosphere for now. I did factor in refraction in my calculations.
Why?
Just to get the general principle across of, like, if you're at the same elevation, it should be zero.
It should be?
Well, in reality, it won't be, right? Because there is refraction. It will be above zero.
The spot you're looking at on the other mountain is the same height above sea level.
Right, we can measure that.
How?
Differential leveling. We can get elevations regardless of the shape of the Earth.
If you're 100 miles inland, how do you get elevation from sea level?
Differential leveling.
Differential level. You're going to have to explain it.
Yes. Okay. You have some point of known elevation. You can start at the sea, sure, right?
Yeah.
But you have some point of known elevation. You stick a rod on that point, right? So you got this 2-meter rod, whatever, sticking on that point.
Uh-huh.
You have another rod 100 meters away. You stick your auto level in the middle, 50 meters in the middle. You look back at the first rod, measure the height on the rod, spin your auto level around, look at the second rod, measure the height on that through the auto level. Whatever the difference is, yeah.
So how do you triangulate the height of a mountain from sea level 100 miles away?
Yeah, that's what we're doing, differential leveling. Right, you take it from one point, you transfer an elevation from one point to the next with an auto level.
And then you assume it's curving, right?
No. Differential leveling does not care about the shape of the Earth. It works fine on flat or curved. In fact, I've got a slide for that, and I'll DM you the slide for that. Hold on. Is it?
After refractions, ignore.
Right. Refraction again. Because you're looking the same. Hang on. You're looking backwards and forwards. Yeah, refraction and curvature will cancel out.
So
you're not even in the water, man.
Right.
You don't even know what your height is.
Let's say the first point on the left is sea level. All right, just start at the left at zero. That's fine.
Let's just say, okay.
I got to go feed doggies in about 5 minutes.
I mean, you're going to have to prove that both of these mountains are the same height.
Yeah, differential leveling gives you correct elevations regardless of the shape of the Earth.
This is a new one on me. So you're talking between two mountains?
Yeah, we're just establishing that we can get accurate elevations. We have a process to do that.
Okay. And the mathematics proves that it will be the same on a flat Earth or a globe Earth, but if you use the globe Earth mathematics, it proves that the Earth is curving.
The two predictions, the two calculations, one of them includes drop and one of them doesn't. That's it.
Right.
100
meters at a time to get 100 miles inland elevation. And 100 miles would have a mile of curvature behind it.
Right, but differential leveling doesn't care about curvature.
I know, right? It's insignificant, even over 100 miles.
It cancels itself out.
Never.
Can you see that it would cancel out on both sides?
No.
You don't understand why it would cancel out?
No.
Let's say you look...
You have to account for the curvature, dude.
No, you don't. With differential leveling, you do not.
I mean, you can ignore it, and then the Earth becomes flat.
No, it doesn't matter what the shape is with differential leveling. That's the whole point.
I think it's just an excuse to ignore curvature.
No. Let's say we're in the middle, and let's say these two rods A and B are a long way apart. And let's say they're a mile apart, right?
Mm-hmm.
Did I explain the process of actually transferring elevation?
Let's say they're 100 miles apart.
Yeah, whatever. Something with a lot of curvature, right?
Mm-hmm.
If I know, let's say I know the elevation of point A, right? I've transferred that from sea level, to point A. I know the elevation at point A. I measure the height on the rod at point A. Then I spin my auto level around and measure the height on the rod at point B. Whatever the difference is between those two measurements, that is the change in elevation, regardless of the shape of the Earth. Let's say the shot from the middle back to A had 8 inches of curvature.
Mm-hmm.
Right? The shot from the middle to B also has 8 inches of curvature. They cancel out.
Do you know how much curvature is supposed to be in 100 miles?
Oh, shitloads, whatever. But do you understand the curvature cancels out?
Maybe if it was over 10 feet, yeah.
No, any distance. Any distance. If you're in the middle, the amount of theoretical curvature will cancel out because you're looking back and then you're looking forward. You're just taking the difference in the measurements on the rod. Have a think about this for a while.
I'm already thinking about it, dude. Like, I don't understand how you can see something from 100 miles away.
Yeah, fuck it. We're not 100 miles away. This is like 50 meters, right? Doesn't matter. But if you want to do it over a mile, and there might be 8 inches either way, do you understand that it will cancel out?
150 feet, that's it?
Yeah, whatever. Doesn't matter what distance.
It doesn't? Yeah. Yeah, okay.
Do you understand the geometry of it? That if you're in the middle, if you're looking to the left and looking to the right, there might be 8 inches of curvature either way. They cancel out. If it's flat, there's 0 drop and 0 drop either side. That cancels out.
So two mountaintops that are 1,000 meters high and a mile apart?
Oh, no, that was just a theoretical, to establish that elevation angle would be 0. It's just an explanation of what an elevation angle is.
Yeah, I know, but you didn't establish that.
Well, if you watch my video, I do real life measurements of these. There's like a dozen measurements in it.
I thought you did. So.
No, we'll feed the dogs in a minute. Yeah, she wants to play Hex Cells, which is the game we're playing. Yeah, but have a think. Yeah, have a think about how that would work on a globe, the differential leveling part.
It can't.
And
oh, bless her. She must be a saint living with you, man. Holy shit.
Say again?
I was just saying, she must be a saint living with you.
My daughter doesn't have a choice living with me. Oh, how'd you get
Oh, it's your daughter? Sorry, I thought it was your wife. Sorry.
All right, sorry.
Daddy, feed the dogs.
Yeah, we'll feed the dogs. Yeah, have a think about differential leveling and why it cancels out both sides of curvature.
Man,
I am thinking about it. I am thinking about it.
Or if you don't account for a curvature, then there's no curvature.
No, the method works regardless of the shape of the Earth.
It doesn't, man.
It does. Think about it. Have a think about it, and I'll chat to you guys tomorrow. All right, we're going to go feed some doggies. Good night. See you.
Enjoy your evening. Take care. Bye-bye.
Tags! What is your profession?
See, old friend, I brought more soldiers than you did.